Good afternoon, everyone. So today we'll be starting the new chapter. The chapter will be the Newton's laws of motion. So let's start with the first very definition of force, right? So here we can see that force is a physical quantity, right? Which either push or pull body and either change the state of motion or tends to change the state of motion or of uniform motion, right? Means let's suppose that we have a body, right? This is the body. Let's suppose the body is of mass m and we are applying some external force F on this body. So this force F either will change the state of motion or it may not change the state of motion, right? If this body is initially at rest, right? So what this force F is trying to do is that it now initially the state of motion of this body is at rest. It means that the body is at rest. We can say the initial state of the motion of a body is that the body is at rest or the initial speed of the body is zero, right? So by rest we mean that initially the body is at rest means the initial speed of the body is equal to zero, right? Now if we apply external force, either we push this block or we pull this block, then what this force tries to do is that it tries to change the state of a motion of a body, right? By changing the state of a motion of a body, we mean to say that suppose if a body is at rest, then the external force may try to uh, put this body in a state of motion, right? Or if the body is in a state of motion, then external force may try to bring this body at rest. Let's suppose that there's a body which was initially moving of mass m, which was initially moving with some speed u, right? Now what I'm trying to do is that I'm applying a force opposite to the direction of the speed of a body, right? If I apply this force opposite to the direction of speed of body, but the initial state of motion of a body is that the body is in motion with respect to some observer with initial speed u, and this force F will try to bring this body at rest, or it will try to change the state of motion of a body to the state of rest, right? So that's what the force does. So the force is nothing; it's an external physical quantity, right? Which when applied to the body, which either change or tends to change the state of rest or of uniform motion, right? It means that if a body is at rest, then the force will try to make this body to be in motion, or if the body is in a motion or uniform motion, then the external force may try to change the status of this uniform motion or will try to bring this body at rest, right? So that's what the force is all about. So force is nothing which is external physical quantity which either change the state of motion or tends to change the state of motion of a body, right? So that's all about the force, right? So force is nothing. Force is a vector quantity, right? Force is a vector, right? Force is a vector. So it will depend. If force is a vector quantity, it will its direction as well as magnitude is of utmost significance, right? And it will follow the vector law of addition, right? If we have to add any two forces, we have to add them according to the vector law of addition, right? So force is a vector quantity. So we'll be treating force as a vector quantity and we'll try to apply all the laws of vectors to this physical quantity as well. Now, the what force tries to do, what are the effects of the force, right? If there is a non-zero resultant force, non-zero resultant force means that the force has some magnitude, right? There is some resultant or the net force acting on the body. Then this non-zero resultant force will try to affect the motion of a body. It may change the speed of a body, right? And sometimes it may not change the speed of a body. It may change the direction of the body only, right? It may change both speed and direction of a body, right? So it may change the size and shape of a body as well, right? So let's suppose that when this force tries to change the speed of a body, right? Let's suppose this body is at rest initially, right? If it is at rest, we can say the initial speed is u. Now what I'm trying to do is that I'm just applying some external force F on this body. Then because of this external force F, after some time this body will be in a motion, right? And it will have some final speed v, right? So it means that the speed of this body has changed because of the action of the external force, right? And similarly, sometimes it may not change the speed, it may change the direction of a body only, right? We can have a case of circular motion, right? Circular motion. So in circular motion, what happens is that if we see in case of circular motion, at every instant, the velocity of the body changes, right? This is the velocity of the body in a circular motion at every instant, right? And you can see that at every instant, the direction of the velocity is changing. If the direction of the velocity is changing, and it's only possible, uh, the change in direction of velocity is only possible when there is some external force acting on the body. And we know that in case of circular motion, there is a force what we call as centripetal force, which continuously tries to change the direction of the velocity of a body without changing the speed, right? So it means that the force sometimes may change the direction of a motion only, and it may not change the speed of a body, right? So here in case of circular motion, only the direction of motion changes, but not the speed, right? But not the speed. And sometimes it may change both the direction and both the speed and direction of a motion, right? We know that in case of projectile motion, right? In case of projectile motion that we studied, both the speed as well as direction of a body change, right? You can see we were initially projecting a body with some initial projection theta with respect to horizontal, and this is how the oblique projectile moves, right? And you can see at each and every point, here the velocity was v, right? Here the velocity was v, and at the highest point, and the initial angle of projection was theta, and at the highest point, the only velocity is v cos theta, right? V cos theta. Only the horizontal component of the velocity is there, or the horizontal component, the speed at highest point is v cos theta only, right? It means that the speed of this body is continuously changing. But not only the speed, the direction of the body is also changing, right? So the only force that acts here is the force of gravity, right? And this gravity, what does this do is that it continuously changes the speed of a body as well as the direction of the motion of a body, right? So here in this case of projectile motion, both speed as well as direction of a body changes, right? And the fourth point is that it may change the shape, and size of a body, right? So let's suppose if we have a rubber band, right? If we have a rubber band and we are trying to stretch this rubber band with the help of some external force, right? If we continuously try to stretch this rubber band, right, and release this rubber band with some by applying some huge forces, right, then what is going to happen is that this rubber band will not regain its original shape and size, right? And because of that, deformation will take place to this object, right? So it means that the external force may produce some permanent deformation or permanent change in shape or size of a body as well, right? So that's the case in the rubber as well. If we continuously stretch the rubber, keep stretching the rubber with the help of external forces, then if we remove the external forces, then what is going to happen? The size and the shape of the rubber body or rubber band is going to change, right? So these are the mainly four effects that a resultant force, non-zero resultant force may produce, right? First point is that it may change the speed of a body. Second point is that it may change only the direction of a body in case of circular motion. And the third point is that it can change both direction as well as speed of a body or motion of a body, right? So that's in case of projectile motion, right? In case of projectile motion, what happens is that both the speed as well as direction of a body change, and it may change the shape as well as size of a body, right? We can have the permanent deformation in the shape as well as size of a body, right? So there are certain laws that this force is based upon, right? That we call as Newton's laws of motion, right? So any motion is governed by some certain laws, right? What we call as Newton's laws of motion. So we'll try to study each and every law one by one, right? So what Newton's first law says that if a body is in at rest, right? First law says that if body is initially in some state of motion, right? and that state of motion cannot be changed unless and until there is no external force acting on our body, right? It means that suppose that we have a body, right? Suppose we have a body of mass m here. If the body of mass m is here and it is at rest, right? The body of mass m is at rest. It means with respect to ground, it is having a zero speed, right? It's not moving at all. So now the state of this body is nothing. The state of body is that it is initial speed is zero, or we can say that it's in a state of rest, right? Now, if we want to change the state of rest to the state of motion, then it can be only done with the help of some external agency, what we call as force, right? With the help of some external physical quantity, what we call as force. So that's what the Newton's first law of motion says, that if a body is at rest, we can only change its state of rest to the state of motion if we apply some external force. And similarly, if a body is in motion, right? There's a body of mass m, it's initially in motion, right? We can only bring this body in motion at rest, right? At rest when we apply some external force on it, or by applying the external force on it to change the state of rest to the to change the state of motion to the state of rest, right? So it means that the state of motion of a body can be changed with the help of external force. If a body is at rest, we can make the body to be in motion, or if the body is in motion, we can by applying the external force, the body can be set at rest, right? So we can change the state of motion. That's what the Newton's first law of motion says. So the body is at rest, then it remains at rest. If it is moving with constant velocity, then it continues to move with the same constant velocity until or unless it's acted upon by external force, right? So that's clear from here with these examples, but actually the Newton's first law of motion says. And there is one more important property of any physical body, right? That's the property of inertia, right? So inertia is nothing. It's actually it is it's nothing. It's just the opposition offered by the body to change its state, right? If the body is in rest, then because of the inertia, the body will be reluctant to change its state of rest to the state of motion, right? Similarly, if a body is in a state of motion, then the body will oppose the change. That's the body will oppose the change from state of motion to the state of rest. That property for any body, any physical body, we call as inertia, right? And one more important point is there is a direct relation between the inertia and the mass of a body, right? We have seen that greater the mass of a body, greater will be its property of inertia, right? So we can say that inertia is a direct measure of mass of a body. If a body is having more inertia, right? More inertia, then it means that the body is actually consists of more mass, right? So we can say the mass of a body is quantitatively or numerically the measure of a body's inertia, right? So numerically, inertia measures the mass of a body, right? So greater the inertia of a body, greater will be the mass of a body, right? Now, based upon three states of motion, we have three definitions of inertia, right? First is the inertia of rest. It means that if a body is initially at rest, its inability to change its state from state of rest to the state of motion. That's what we call as inertia of rest. And similarly, if a body is initially in a state of motion, then if we try to bring this body uh, to the state of rest, then there will be a position from the body. That's what we call as inertia of motion. There will be a position or inability of a body to change its state from state of uniform motion by itself to the state of rest, right? That's what we call as inertia of motion, right? Similarly, the inertia of direction, that's the inability of any body to change its direction of motion by itself. And we know that any body cannot change the state of rest on its own. Any body cannot change the state of motion on its own, and any body cannot change the state of uh, direction of motion on its own. So for all the things to change, be it state of rest, be it state of motion, be it state of direction, right? We need to apply some external force, right? And this inability of any body to change its state, right? To change its state of motion is what we call as inertia of a body, right? So these were the three types of inertias we studied. That's inertia of rest, inertia of motion, and inertia of direction, right? So let's move on to the next part of this chapter, that's the linear momentum, right? The linear momentum is nothing. It actually measures the amount of motion possessed by a body, right? It's nothing. It's the amount of motion possessed by a body, right? That's what we call as linear momentum, or that's how we measure the momentum of a body. So momentum indirectly or directly uh, gives us an idea about the motion possessed by a body, right? So mathematically, we define it as the product of the mass and velocity, right? And velocity, we know it's a vector quantity. Velocity is a vector quantity, right? If velocity is a vector quantity, then momentum has to be vector quantity, and the direction of the momentum will be nothing. It will be the direction of the velocity vector, right? So it means that momentum is nothing. It's the product of the mass and velocity, right? It means greater the mass of a body, greater will be its momentum, and greater the velocity of a body, and greater will be its momentum. Or we can say that small particles may have large momentum because of its large speeds, right? Or large velocity. Or similarly, slowly moving bodies may have large momentum because of its large mass, right? So the equation illustrates the momentum is proportional to an object's mass and directly proportional to the object's velocity, right? And the direction of the momentum vector is same as the direction of the velocity vector, right? And momentum of a body is actually represented by P, right? Momentum of a body is represented by P. P is the symbol for momentum, P vector. We can write it as M times V vector, right? MV vector. So this is how we write the momentum of body. It's mass times the velocity vector. That's the momentum of a body, right? Now the question is, we can just there's a small question that a block having mass 2 kg moving with velocity 2 I cap plus 3 j cap, but the momentum of the block, right? So the momentum of this block is nothing. It's the mass times the velocity, right? Mass times the velocity will be the momentum of this block, right? So mass times the velocity will be the momentum of this block, and velocity vector has been given as velocity vector is given as that's equal to 2 I cap plus 3 j cap, right? It means that it will have two components of the velocity, one along the x direction, another component along the y direction. If it is having two components of the velocity, one along x, one along y, it means it will have two components of the momentum, one along x direction and another along y direction, right? So we can just write momentum can be written as mass times the velocity, right? Velocity. Or we can write it as m times vx I cap plus vy j cap plus vz k cap, right? So it will be nothing. It will be mvxi cap plus mvy j cap plus mvz k cap, right? It means that momentum will have three components here. Mvx will be px I cap, right? And mvy will be py j cap, and mvz will be pz k cap. So we can also write this momentum in component form like this, like we write the velocity, right? So here we have to calculate the momentum. Momentum will be nothing. It will be equal to P times mass is 2 kg. So it will be 2 multiplied the velocity. That's 2 I cap plus 3 j cap, right? That will be equal to 4 I cap plus 6 j cap. So this will be the final momentum, right? If we have to calculate the magnitude of this momentum, that will be equal to root of 4 square plus 6 square, right? 4 square plus 6 square. So it will be 36 plus 16. That will be equal to 52, root 52. So this will be the magnitude of the final momentum, right? Magnitude of the final momentum. Let's assume that this value of the momentum is in meter per second, right? Not in kilometer per second, right? So velocity is in meter per second, not in kilometer per second, right? And similarly, we defined change in momentum as. So change in momentum is nothing. It will be defined as change in momentum will be defined as final momentum vector minus the initial momentum vector, right? Change of any physical quantity is defined as final minus initial. That will be the change in any physical quantity. And similarly, we have change in momentum, and it will be defined as final momentum vector minus the initial momentum vector, right? So let's, based on the change in momentum, right? Now the question is that change in momentum, if the momentum changed by the momentum of a body change, and it's very obvious that if the momentum has changed, then the velocity vector of the body has changed, and the velocity vector can only be changed. It means that the state of motion of a body has changed. And the state of motion of a body, we know that can only be changed when there is some external force. So if momentum has changed, then definitely there has to be some external force because the state of a motion of a body has changed, right? So that's according to Newton's first law, right? Now let's try to solve this question. The question is that a ball of 0.2 kg, right? 0.2 kg hits a wall with a velocity of 25 meter per second, right? The initial speed of this wall, the initial speed of this body has been given as 25 meter per second at an angle of 45 degree with the horizontal, right? So it's moving at an angle of 45 degree with the horizontal, right? If the ball rebounds at 90 degree, right? The ball rebounds at 90 degree to the direction of incidence. Calculate the magnitude of change in momentum of the ball, right? So the situation is like this. The situation we can draw here. The situation is like this. Suppose that this is a wall here, right? This is the wall. This is the wall here. And ball is approaching to this wall like this in this direction, right? The ball is approaching this wall in this direction. Let's suppose this is the direction. And what happens is that when this ball strikes this wall, it is reflected back in this direction, right? In this direction in such a way that this reflected direction is actually perpendicular to the initial direction. So it will be like this. It's actually perpendicular to the initial direction. So we can write it as initial velocity u here and final velocity v here, right? And one more condition is given that it's given that it is rebounded back with the same velocity, right? Same speed. It means that if it was initially approaching the speed of 25 meter per second, right? And it once again leaves with the same speed uh, of 25 meter per second, right? And this angle has been given here as theta, right? This angle has been given here as theta. So this is the theta angle here, right? And this is also the theta angle here, right? And we know that according to laws of reflection, if this is a theta, this has to be theta, right? Because ball has been reflected back, right? So if this is the angle at which it strikes the surface of this wall, right? That's theta, and it has to rebound back with the same angle, theta, right? So it means that this theta plus theta, it has been given that it actually rebounds back perpendicular to the initial direction. It means that theta plus theta has to be 90 degree. It means twice theta will be 90 degree, or we can say that theta is nothing, it's equal to 45 degree, right? So theta is equal to 45 degree, right? So theta is equal to 45 degree. It means that if theta is equal to 45 degree, this theta angle here is 45 degree, right? We can just resolve where to calculate the change in momentum. We can just resolve this velocity vector into two components. One component will be along this and another component will be along this. So it means that we can write this initial velocity vector with, if this is theta, then this angle has to be theta, that will be 45 degree, right? So this velocity vector has to be equal to, it will be equal to 25 cos 45 degree, right? I cap. And this is second component that's along minus j cap, it will be 25 sine 45 degree j cap, right? And similarly, our final velocity vector will be equal to, you can also resolve it into two components. One component will be along here and another component will be along here. And this component is also going to be equal to v cos of 45, right? and this component will be here p sine of 45. So we can just write here it as 25. Since this direction is taken as positive, this direction will be negative, so we'll just take it as minus 25 cos 45 degree I cap, right? And minus 25 sine 45 degree j cap, right? So similarly, if this is the final velocity vector, we can write the initial momentum pi as, so the mass of this body has been given as 0.2 kg, right? So the initial momentum will be 0.2 multiplied by this 25 root 2 I cap minus 25 over root 2 j cap. And this final momentum will be nothing. It will be equal to 0.2 minus 25 over root 2 I cap, right? Minus 25 over root 2 j cap. And the change in momentum delta p will be nothing. It will be equal to final momentum vector minus initial momentum vector, right? So you can just subtract the two vectors. So it will be 0.2 minus 25 over root 2 I cap minus 25 over root 2 j cap. That will be final minus initial. That will be equal to 0.2 25 over root 2 I cap, right? So it will be minus 25 over root 2 j cap, right? So the change in momentum has to be equal to, so you can see here that the y component will just cancel out because it will be minus 0.2, that will be plus 25.2 into 25 by root 2, so it will be plus here, so it will get cancelled, right? So it means that we are left only with the x component here. So the x component, it will be minus 2 times 0.2 multiplied by 225 over root 2, and it will be along I cap, right? It will be along I cap, right? So this will be the final momentum, or we can write it as, so we can write it as 0.4 multiplied by 25 over root 2 I cap, or we can write it as, so 25 multiplied by 0.4 has to be equal to, it will be equal to 10 over root 2, right? Minus 10 over root 2 I cap, right? So this will be the final change in momentum, right? For this question. So this will be the final change in momentum for this question. It is just, what we have done is that we have just used the concept change in momentum will be final momentum minus initial momentum. We have just represent the initial momentum with vector and final momentum as well with vector, right? And one important point you can see here that here only the component which is perpendicular, the component which is perpendicular to the wall initially, the component which is perpendicular to the wall, that was the x component. It means that just the x component gets reversed, right? There's no effect on the y component, right? There's no effect on the y component of the velocity, right? It's just the x component of the velocity which gets reversed. It means that there will be no change in momentum along y, right? The only change in momentum will be along x direction, right? It means that whatever force is acted on the wall because of the wall will be along x direction only, and there will be no force along the y direction of the wall, right? So that's what do we mean by here, by not changing the component of velocity or component of moment along y direction, right? So let's move on to the second law of motion. The second law of motion states that, if a momentum of a body changes, right? If a momentum of a body changes, then momentum, by changing the momentum of a body, it means that the state of motion of a body has changed. And by changing the state of motion of a body, it means that it can only be changed. The body cannot change the state of its motion on its own. It will change its state of motion with the help of some external force, right? Now we have to just quantify this external force, how much this external force is, and how this external force depends upon the momentum, and it is formulated in Newton's second law of motion. So the Newton's second law of motion states that the external force, net external force acting on the body is nothing. That's equal to, that's directly proportional to the rate of change of momentum with respect to time. That's dp over dt. So this is the external force acting on the body. That's the external force is directly proportional to the rate of change of momentum with respect to time. Or we can just replace this proportionality constant of proportionality with constant k. That's k dp over dt, and this constant of proportionality has got value k equal to 1, right? So it means that Newton's second law states that force is nothing, it's equal to first derivative of momentum with respect to time, right? So that's what the Newton's second law states. So second law states that rate of change of momentum, uh, the force is directly proportional to the rate of change of momentum with respect to time, right? So this is nothing. This is the second law of motion, right? Second law of motion. Second law of motion. We can rewrite this equation as, we know that momentum is nothing, that's equal to m into v, right? M into v. So this is our momentum, right? So if we substitute the value of p in this equation, so our f will be nothing. It will be equal to d over dt of d over dt of mv, right? So it's nothing, the product of the two physical quantities, right? And we have to take the derivative, so it will be m dv over dt, right? Plus v dm over dt, right? That means that we have two components of the force actually, right? One will be because of the change in velocity, and one another force will be there because of the change in mass, right? Because of the change in mass with respect to time, right? Change in mass with respect to time. If the mass of our body is changing with respect to time, then also force is acting on the body, right? It's not possible without force, right? And similarly, if a velocity of a body is changing with respect to time, then also the force is acting on a body, right? But if we assume that the mass of a body does not change, if mass is a constant, right? M is constant. If M is constant, if M is constant, then mass will not change. So dm over dt has to be equal to 0, right? If dm over dt has to be equal to 0, then we can just rewrite this equation as F is equal to m dv over dt, right? And dv over dt is nothing, is the rate of change of velocity with respect to time. We define it as acceleration. So m will be equal to a, right? So force will be equal to m into a, right? So this equation is nothing. It's one of the outcomes of Newton's second law of motion, right? So this is not a Newton's second law, right? This equation is not a Newton's second law. It's very incomplete equation with respect to the Newton's second law of motion, right? The complete equation of the second law of motion is this, right? This is the complete equation, right? You can say this is the second law of motion. This is one of the outcome of the second law of motion. We are assuming here that the mass of a body does not change, right? If the mass of a body does not change, then only we can apply this equation, right? So only applicable, only applicable if m is constant. If m is constant. If mass of a body is not a constant, then we cannot apply this equation. Then we have to go by this equation. That's F is equal to dp over dt, right? That's the basic form of the Newton's second law of motion, right? That is the fundamental form, right? So this equation can only be used to calculate the acceleration of a body if the mass of a body is constant, right? F is equal to ma, right? So from here we can see that the SI, if we talk about the SI unit is nothing. SI unit will be meter per second. It will be kg meter per second square, right? Kg meter per second square, right? Or we call it as Newton, right? This is also called as Newton, right? So this is nothing. This is the second law of motion. So second law of motion is nothing. It's dp over dt. It's the rate of change of momentum with respect to time, right? Right? And F is equal to ma is only valid if mass of a body is constant, right? So let's try to solve this question here on the screen. A cricket ball of mass 150 grams is moving with a velocity of 12 meter per second and is hit by a bat. so that the ball gets turned back with a velocity of 20 meter per second if the duration of contact between the ball and the bat is 0.01 second. Find the change in momentum and the required force, right? It means that initially the ball was moving, the ball of 150 grams was moving with a speed of 12 meter per second, right? 12 meter per second. And the mass of this ball is nothing, it's 150 grams, or you can write it as 0.15 kg, right? Now what happens is that at some point here, and this ball has been hit with a bat, right? With a bat. So this ball has been hit with a bat. When this ball is hit with a bat, its direction gets reversed, and the speed now becomes 20 meter per second, right? The mass of the body is same, that's 0.15 kg, right? Right? And the time of contact between the ball and bat is given as delta t, that's equal to 0.01 second, right? It means, what does it mean? Delta t is equal to 0.01 second. It means that this much of time has been taken to change the momentum of a body, or change the velocity of a body from 12 meter per second to 20 meter per second, right? So the change in momentum, it's once again nothing, it's equal to final momentum minus initial momentum, right? Final momentum minus initial momentum, right? So if we write the initial momentum pi, that has to be equal to, the body is moving along the x direction, right? Positive x direction. We can write its momentum as 0.15 multiplied by 12 along I cap. And final momentum, the body is moving along negative x direction, so it will be minus 0.15 multiplied by the 20, right? So it has to be equal to I cap once again, right? Or we can write this p initial momentum as, right? So it's along I cap, right? So the change in momentum will be nothing. That will be delta p. That will be p final minus p initial. That will be 0.15 multiplied by 20 I cap minus 0.15 multiplied by 12 I cap, right? So it will be equal to minus 0.15 multiplied by the 32 I cap, right? Correct. So it will be minus 1.5 multiplied by 3.2 I cap, right? So this will be the change in momentum, right? This will be the change in momentum. If this is the change in momentum, then to change this momentum, the force must apply on this body, right? And the force acted on this body for this shorter duration will be nothing to be delta P or delta T. And delta P has been given as 1.5 multiplied by 3.2 I cap, right? Over the time, that's 0.01 second. So this will give us the force acted on this body during this small duration, 0.01 second, right? And to change the momentum of this body from 12 meter per second along positive x direction to the 20 meter per second along negative x direction, right? So this is how we can apply the Newton's second law to calculate the force acted on a body, right? So let's try to solve this question as well. The question is that momentum of a body, momentum of a particle is given by p is equal to, so here the momentum is given actually as p is equal to at square minus twice bt, right? This is the momentum of a body. Now the question is, find the time at which the force on particle becomes zero. So we have to find the time at which the force on the particle becomes zero. So we will first of all calculate the force. Force is nothing, it's dp over dt, right? Dp over dt, it will be equal to d over dt of at square minus twice bt, right? So it will be derivative of t square will be 2t, so it will be 2at minus 2b, right? Because derivative of t is 1, right? So we have to calculate the time at which this force becomes 0. So we'll just put this f equal to 0. That's equal to 2at minus 2b, right? So from here you can see that our value of t will be nothing. It will come out to be b over a. So this will be the time after which the force acting on this body will become 0, right? So b over a will be the final answer, right? So let's try to solve this question as well. The question is that a force of 50 Newton acts on a block in the direction as shown in figure. The block is of mass 5 kg resting on a smooth horizontal surface. Find out the acceleration, right? Now this block, it's given that this block actually moves in the horizontal direction only, right? If this block moves only along the horizontal direction, you can see that the acceleration is along horizontal direction. It means that the only force that will be responsible for this block to move along the horizontal direction will be the horizontal component of this force, right? Horizontal component of this force. We can just resolve this force into two components, right? Into two components. If this is 60 degree, then this has to be 30 degree, right? And this component will be 50 cos 30 degree, right? And this component here will be 50 sine 30 degree. So the only force responsible for the horizontal motion will be the horizontal component of the force, right? So the acceleration along horizontal direction will be produced by the horizontal component of this 50 Newton. So it means that this acceleration A will be nothing. It will be equal to 50 cos 30 degree, right, upon the mass of this block. And the mass of this block has been given as 5 kg, right? 5 kg. So we can just cancel out this. So it will be 10 cos 30 is nothing, it's root 3 over 2. So the final acceleration along horizontal direction will be 5 root 3 meter per second square, right? 5 root 3 meter per second square. So this will be the acceleration of this block along the horizontal direction, right? This will be the acceleration of the block along horizontal direction. So let's stop here. And we'll be in the next lecture, we'll be discussing more about many other physical quantities. We'll be discussing about impulse in the next lecture. And then we'll be starting to discuss about the types of force, all the types of force that exist around us, right? So that's it. Let's stop here. Let's meet in the next lecture, right? So take care.